Hello, once again, pre-calc students. Section 7.1 notes brought to you by Lego Monkey. So, back in chapter 6, we learned everything trig. And what we're going to work with now is a couple different types of identities, specifically the Pythagorean identity, which is like one of the most important ones, and then the sum and difference identities. So, just a real quick review. When we say identity, we mean statements of equality that are always true. And so these were a set that we had developed back in chapter 6. So we know that sine x equals 1 over cosine x for all x values within the domain here. And cosecant of x equals 1 over sine x, and so on and so forth. We noted these little ones, blah, blah, blah. This was a pretty important one, tangent x equals sine over cosine. So now we're going to extend these. And for those of you that have seen me in person, this is the point in my high school career that I decided to be a math teacher. When I encountered these identities, they were just glorious. We wrote them on the chalkboard. It was amazing. Okay. Anywho, so let's recall something real quick. For the unit circle, we noted that an equation for that unit circle was x squared plus y squared equals 1 squared, because the radius of a unit circle is 1. Let's remind ourselves of that. And the center of a unit circle is 0, 0. So that equation of circle simplifies to this. Now, also we know the x and y coordinates of any point on the circle can be written as, x equals cosine of theta, and y equals sine of theta. So if we smash these two things together, our notion of what x is equal to and what y is equal to, we will replace the pieces in this with these values, and we'll get a new identity that is always true. So we'll put in, let's see, we've got this squared, so x squared plus y squared equals 1 squared, and we're going to input there for x the cosine of theta, and for y the sine of theta, and there it is. So the notational way, the typical way we write these things, is we put the squared in between the cosine and the theta, because we don't want you to think that this is cosine of a theta squared. If we had put it outside, you could also use these parentheses if you wanted to, and then sine squared theta equals 1. So that's this new Pythagorean identity. It's a wonderful identity. So in trigonometry, and then all subsequent areas of mathematics, we use particular notation to denote raising a trig function to a power to avoid confusion. That's what I was talking about. So if I want, say, the square root of sine, and I want to write it in exponential notation, I would write it like this: sine to the 1/2 power of theta. That's similar to writing sine of theta parentheses to the 1/2 power. We just tend to use this one. This is the preferred one. Likewise, if I want cosine cubed, so cosine cubed, we tend to write it this way, because that's different than, say, cosine of an angle cubed. So we have to be careful of the difference between these two notations. It's also similar to, if you recall, the inverse function was denoted this. That was a notational way of writing it. And then we also noted that if we had like x to the -1 power, that was 1 over x. So here, these represented operations. This represented a notational thing. And these are operations, but this is how we write it. Okay, so with the sine squared plus cosine squared theta equals 1, that's called the Pythagorean identity. We can use any variable we want for theta. We could use x, we could use y, we could use theta, anything we want. So we're going to create 2 more identities. Don't look at the bottom of the page yet. Using this sine squared theta plus cosine squared theta. And the first one we're going to do is divide this equation by sine squared theta. So let me rewrite it. And then I'm going to divide everything by sine squared theta. And then we're just going to simplify our results. Well, sine squared theta divided by sine squared theta, that's a 1. And then I'm going to write this first this way, and then I'll apply a basic trig identity. So the basic identity we're going to apply here is that when we have cosine over sine, we knew that was cotangent. Well, we could just replace squareds in all of these, and we get the same relationship. So cosine squared divided by sine squared is cotangent squared theta. Similarly, 1 over sine squared theta, let's see, 1 over sine was cosecant theta. So now if I make these squareds, 1 over sine squared theta would be cosecant squared theta. And there it is. There's a new Pythagorean identity. 1 plus cotangent squared theta equals cosecant squared theta. Wonderful. Let's do it again. I think this is a typo because if we divided by the same thing we just divided, we'd get the same result. I think what we want to put here is cosine squared theta. So I'll rewrite my Pythagorean identity. And now I'm going to divide the entire equation by cosine squared theta and see what we get. This one I'll do with a few less steps since you've already seen me mess with it up here. Sine over cosine squared is the same thing as tangent squared theta. This is the same thing as 1, and then 1 over cosine squared theta is secant squared theta. And there's the new identity. Isn't it beautiful? So here's the 3 Pythagorean identities. Sine squared plus cosine squared equals 1. 1 plus cotangent equals cosecant with the squareds. And 1 plus tangent squared equals secant squared.